Hello, everyone. I am Armand, the CEO of Properate. This is the launch of our white paper. It's something that I think we have been seeing coming for a long time. I have been in the industry for about 7 years. This is, I feel, one of the best summaries that we could create for the issue that we had at hand, and we are going to talk about it. So we're going to talk about what our company essentially is hoping to achieve in the community scale across Canada. So that's the purpose of this study. We are going to talk about the energy modeling landscape within Canada and worldwide. We're going to talk about technology overviews when it comes to building energy rating, energy modeling, and then provide, as Arthur mentioned, a study of about 7,000 homes that we assess this energy rating engine that we have and lay out the foundation for the further work. Okay, so a bit of an introduction about who we are, what we do at Properate. Our mission as a social purpose organization is to assess and improve home energy performance wherever we have the opportunity. So this is typically what we call Part 9 residential homes, which we feel like they are an overlooked part of the building stock, but they have huge potentials for performing deep energy retrofits, home energy upgrades, and they can really push forward the climate and also social actions that Canada has. To make that happen, the first step for us is to find homes with the highest potential. So the homes that spend a lot of energy, they have a lot of low-hanging fruits where efficiency can be improved. And then after that, also encourage the homeowner's action. Now, these two are not necessarily separate things, because if you lower the barrier for the homeowners sufficiently enough, they can, do things, assess their home in a DIY fashion, or have a really interactive and delightful interface where they can understand their home's performance. Then these things all are going to fit into each other. And we think this all starts with creating digital twins of entire communities. So if you take a look at the video on the right, we have a number of homes in the landscape. For each individual one, if we have an idea of what is the condition of this home when it comes to energy efficiency, energy consumption, and also have an idea about where are the areas for improvement, then have this kind of model for every home within the entire community. Then we can go on and start looking at the potentials, and also really have answer to questions that have been previously impossible to answer. For example, how much resources would it take to bring a community to net zero? So over the next half an hour, we are going to talk about all of these. But first, let's start with how we have been doing this in the past. And energy rating is essentially the industry term for figuring out where each home is. If you read our white paper, we have had 3 particular regions that we highlighted, but it is more of a broader scope for us. Looking at this, we are seeing a lot of interchanging words, kind of sometimes confusing between rating, auditing, and labeling. We are going to just use the word rating. We think that makes the most sense. Everyone kind of understands what it says, but it's not to say that it is any different from having a condition assessment, a complete and thorough condition assessment of a home, and also having the home's energy performance known within a certain region. So part of it, kind of a disclosure labeling. So we kind of think of these 3 things as one when it comes to our purposes. We see that in the industry, energy rating is technically usually backed by energy calculations. They can be very rudimentary, or they can be a full-on building energy model. The objectives are very varied. Like in Europe, they like to have it, for example, a score of a home being B or C or A, just finding that general label. And sometimes the objective is to have actual usage. And also fidelity of how much data is being collected varies substantially. For example, in the UK, the home visits are much faster compared to what we have across Canada. The amount of data that's being collected is more generalized, more streamlined, essentially. And the fidelity really is a trade-off here. In some communities, in some jurisdictions, they tend to not really have the capacity for going for higher fidelity. Sometimes it's because of the costs. Even in Europe, that has all of the EPCs being under the same program overall, some of the countries require a on-site visit, but not all of them. So the same thing can be done without a site visit. And that graph you see at the bottom is an explanation of different costs across European countries. So very much varied, and some of that is really putting a cap on the possible fidelity because of the market conditions. But in general, there are, when it comes to this fidelity versus the cost or effort, basically trade-off, we have seen 3 levels of rating. The first one is virtual rating, which is instant. It doesn't require any kind of homeowner intervention. You can go and look at some sort of public data and then expand it to the community level. Try to extract as much energy efficiency insight or energy consumption insight from it, and then assign a score to every building. Then remote rating takes it one step further. It can be something that's just not on site. It can be a professional having a Zoom call with a homeowner. It can be doing it the questionnaire manner that we do it. But it takes a little bit of an involvement, not a substantial amount of involvement, but a slight amount of involvement from the homeowner. Better yet, if it's all automated, so they don't really have to wait for anyone. And the purpose of it is qualification. And then the next step of rating is on-site rating type, which is the most comprehensive, the highest level of rating, which brings the biggest accuracy. It brings in the professional on the site, so they can really look at all of the specifics of that particular building. But it also requires a lot of involvement from the homeowner. It's not an instant, so 3 hours on site, 3 hours off site. It's going to be some hours before any kind of insight is extracted from that assessment, from that rating. Now, being a Canadian company, of course, our first and foremost interest is rating in Canada. The EnerGuide system in Canada is done on site. Rating is backed by a complete energy model, which is a huge plus. Like, this is not a simplified, generalized case. There is a actually 1,4D tested energy model that is supporting the label that's being generated, which we think is great. And the software being used for the rating is called HOT 2000, slightly, decades old software. And it is using the EnerGuide rating system, which is the specific set of conditions that the EnerGuide program has set out so that the label remains comparable between different homes and between different assessments. Now, what we find in this Canadian standard is that it is very good for verification of what the condition of the home is, but it's not fit for community scale rating, that digital twinning at the scale that we want it to be. So that takes us to the technology review, essentially going back and trying to see, okay, what is available out there and what are our priorities to perform, like find or build our, boosted, improved rating system. So going back to the purpose, digital twinning entire community, we set out 4 ideal criteria that we want to see in a rating tool. That we wanted to set out for ourselves. This criteria is, the first one is reproducibility, meaning that if I have data from one home collected, I give it to a rating tool, I want to get the same result every time that I give the results to the rating tool. Now, this might seem like a very obvious thing, but it is not necessarily the case. There are Monte Carlo based machine learning algorithms or random based statistical methods that actually violate this criteria of reproducibility because of the way they are designed. But I would say this is probably the simplest criteria that a tool can meet. Now, moving on to expandability, we also wanted to have a rating tool that does not rely on the data from the past. Now, the reason this is important is because, first of all, we are seeing that our climate is changing a lot of the time. The energy modeling, the rating is dependent on the climate. So you are dealing with new weather files or future weather files, stuff that have not been available in the existing data. The second reason being is being the inclusivity of it. Low-income housing, specific types of housing may not have as much energy assessment done in the past. We really want a rating tool that is kind of forward-looking and having the ability to deal with unseen, quote-unquote, buildings. The third criteria, it comes down to auditability. So auditability really is how can we look under the hood of this rating tool, understand where the results are coming from. So if it must be explainable with some tested software, something that is such as ASHRAE 140 tested software, or like there needs to be some kind of an insight at the component level that we can look at and say, okay, so this is working as intended. And last but not least, it must require minimal hardware, and that is simply because we are looking at, when we are looking at community scale ratings, we are looking at thousands, tens of thousands, sometimes millions of homes. And the particular use case that Properate has is not necessarily only just condition assessing the existing home, but also looking at alternative methods of doing deep energy retrofits, looking at all of the potentials of doing energy upgrades for every home. So this is going to easily push the amount of energy ratings and energy modelings that we need to do a lot higher. So we need to have a very efficient tool for that purpose. So there are three different rating technologies that they're fairly common in the energy rating, energy modeling industry, and this has been the case since I remember it pretty much. And we kind of try to look at the solution that we wanted in terms of this spectrum in the first place. And the spectrum is white box to black box energy models. So literature suggests that white box, the name is coming from the energy modeling tool being transparent, meaning that if you want to model a building, it's completely physics-based. Now we get into what that exactly means. But also, black box being statistical based, and the name black box comes from the fact that it's kind of opaque and it uses either regression or some kind of a statistical model to kind of figure out the building energy rating when you're looking at a building. And then anything in the middle of this is considered gray box, any kind of hybrid. So what does that exactly mean? The white box models, they are really focusing on how the building physically works. And they look at it in that sense, they try to simulate the real world conditions as closely as possible. So let's say we have a energy modeling tool that is, we want to use it for energy rating of a home. We start to run it. So what it does is that it picks up the first day of the year, the first timestamp it has, maybe it is like a time step, could be like every hour, it could be every day, it could be a fraction of a day. So it picks up the first one, let's say it is on January 1st at 7 a.m. Now, the energy model has some data from the climate. It has some data, for example, in the EnerGuide rating system about the occupants. And also we have given it information about the home, about the envelope of the home, the R values, the shape of the home, and all of that. So it starts to model all of these together. So it says, for example, okay, at this time of the day, this much sun is coming through. This is the outdoor air temperature. X many number of people are in the home. The amount of heat loss from the envelope is this amount. So it basically builds out the model for the first time step, and then moves on to the next time step based on the previous conditions. It also adds what has changed in the time step, and it starts to re-simulate this. So for example, if it's at 3 p.m., it will be like, okay, so now the sun has moved, it's somewhere else in the sky, the temperature is different, it might be a little warmer. Occupants may have left the home, they may not be inside the home. So then it will use all of these things to modulate the amount of heat loss, heat demand that it sees in the model, and then just use that for the next time step. Very iterative, very continuous, but eventually it tallies up all the results, says, okay, overall, over all the time steps, over everything, I have seen this much energy loss, I have seen this much occupants, using different equipments, I've seen X amount of solar gains. That leaves me with a number which becomes the energy rating. So the overall demand of a home in this case is 109 gigajoules. Looking at this as a diagram, we see that the white box models are very iterative. They are computationally very intensive, meaning that every time step they have to go over all of the components that are inside the model, and then try to calculate a heat balance calculation. And then if it impacts other components, they have to go to the other components, they have to recalculate them until they are reaching a level of certainty about the first time step, and then like just move on to the next time step, and then they have to keep doing the same things over and over again, incrementing between the time steps. So this part becomes very computational. This middle part becomes computationally intensive. And then finally, when that's all done, then they can report on the time steps. So because of that challenge, they really don't pass our lightness test. There are older energy modeling tools, for example, such as HAL 2000 in our example, that are built pretty lightly in terms of the computation they do because of the hardware requirements at the time that they have been built. So they do a lot of generalization, they make things a lot simpler. But in the meantime, they are not optimized for modern hardware. So they cannot really use multi-core processes. They cannot leverage hardware abilities that modern computers have. So they also like fail the lightness test in different ways. But in general, even when you make a trade-off with the white box model and try to make it lighter, it can impact auditability. So usually when we are looking at very comprehensive white box modeling tools such as Energy Plus, which are very detailed about all of their outputs and they are very auditable, they have to kind of take off that lightness from their objectives. Now, because white box have been kind of having all of the other criteria except for the instant computation, possibilities, there are some solutions that have been used in the industry to deal with that issue. Let's say, for example, you want to simulate a community. What you can do is to scale the computation. So use a supercomputer, use a cloud cluster. For example, the Argonne National Laboratory in the US, they use a supercomputer to perform energy rating for 178,000 buildings. That's how they really solve the problem. We think that might be a good like one-off solution, but if you want to constantly do energy rating based on newest technologies, newest climate data, everything, it becomes a bit of a hassle. The second one is to define and simplify the use case. So for example, if you want to create formulated upgrades for every home, there can be archetype studies, which instead of studying entire homes in the community, we can look at what homes are the most similar to the archetypes that we have found, which is like the typified standardized homes. These are kind of the averaged out homes of the community. And then instead just go and study those archetypes. The last solution, the last class of solutions that we specifically had identified was interpolate between known white box results. So let's say you have an energy model done for, you have like, for example, 40,000 energy models ran through a white box system. And then you have a new home that, has its own unique characteristics, but individual characteristics are somewhat similar to the homes you already have the results for. that tools such as, for example, Episcope in Europe or CBAT, they can go on and start to find which home is the most similar, which known home, which labeled home essentially is the most similar to your queried home, and return back that result. But with the developments of statistical models, this last thing also has gotten its own branch historically in building energy assessments. And that is with the other side of the spectrum in the energy modeling, and that's the black box. This really talks about that opaqueness of the energy modeling, and we're going to get to why. But instead of like just looking at it in terms of an energy model and try to understand how reality works and simulate it, the black box models have a very purely statistical approach to the problem. So, for example, in the table that I put here, we have some information about each building. We know what the area is, we know what the location is, the number of windows, roof types, heating, etc., etc. And then for each of these homes, each row is being one home. We know when somebody has gone and done the energy rating of it using a white box model, like such as HOT 2000, such as Energy Plus, the rating result has came out to be what you see in the last column. But then we have one home, we don't know what the rating is going to be if we were to run it through HOT 2000 or something similar. So what we will do is that we give all of this data to a machine learning model, to an artificial intelligence system, to a regression model, something that has to do with statistics, and then we query this rating. So we kind of try to make it understand all of the relationship between different things and the rating. And then we give it a query home, and hoping that based on the relationship it has learned, it can give us the rating back. Looking at the architecture of this system, it gets a lot simpler. So you basically have inputs, you try to sidestep the whole physics computational calculation, you try to make the model you have understand what a building is without explicitly telling it what a building is, and then you get the model outputs. Now, of course, this black box can be a lot more complicated. It can be very substantial, or it can be a very simple model, but it's really out of the scope of the overall energy modeling pipeline, what's happening there, and hence the name black box. Looking at it, comparing it with the white box model, the simplification is really evident when it comes to all of that iterative calculations. It really does pass the lightness test because it is very fast. It can be very fast in the way that today modern systems are being designed. Moreover, you can parallelize results. You can use modern hardware capabilities, even sometimes GPU acceleration to get to results. So it's a lot faster and lighter. But for other criterias, there are either like certain shortcomings or outright missing the point. So for example, if you want to reproduce results, there are a lot of AI models that work based on some randomness, some noise being given to them for getting the results out. Mention an example of a Monte Carlo system. Those ones already failed the test. Then for expandability, by definition, AI models or machine learning, any kind of black box model, is looking at the data from the past. So in our example, we had this table. So we had all of this data from the past. Now, if this data has been collected based on a previous climate file, or it has been assessed based on certain types of, before a certain kind of jurisdictional or modeling guideline changes happen, we can't really query the new case in a meaningful way. So they are reliant on the past data by definition. And lastly, they are not really auditable. By the definition of this black box system, we really cannot peek into and understand what is going on. There are just a number of matrix multiplications that are happening, or some kind of a statistical method that's happening in the system. And the nature of that statistical method is really unknown to the outside observer. I also provided a rudimentary example here that we have that further explains why the expandability is not the case. If we have a regression here, that we have, like from a model, in this case, we put a rudimentary example of a floor area and EnerGuide. When a new data point gets added here, the regression line, of course, like changes substantially. And if you look at the beyond point C, the trend line that used to be going down, now it's trending upward. So the model's objective is to try to fit within the known conditions that it has and nothing beyond that. Now, this matters because, for example, we talked about low-income housing. We talked about buildings that haven't been modeled in the past. This can be a really big shortcoming here because we really are not able to look beyond what has been seen before. Finally, we get to a gray box system, the hybrid that we have made between black box and white box models. That kind of was the basis for our rapid building energy simulation tool, or in short, we call it R.E.A.L. Think of it as looking at all of the conditions of the building all at once. So we don't really have to do what the white box or black box models do well explicitly. We can combine the two together and really have a system that takes the best of the both worlds. So we build out our model in a white box fashion. We really have a good understanding of what different building components are and how the system of the buildings is supposed to tie in together. We just swap the very computationally intensive parts of the white box systems with the efficient parts of the black box model. And that really speeds up our computation. And we think this kind of hybriding between the two extremes has a lot of potential on delivering on all of the criteria, on all of the 4 criteria that we had. Therefore, like doing a summary, like gray box models are not necessarily like a one-size-fits-all solution. They are not a holy grail on its own, but for the 4 things that we set out for ourselves, we think that they excel in the way we have designed it compared to the other 2 extremes of the energy models. Now, I'm going to pause here again in case anyone has a question. Just going to give it a 1-minute breather. So feel free to put your questions in the Q&A or in the chat. Okay, so 2 questions here. The first one is about examples. So there are many examples in the literature about different white box, gray box, and black box models. Wouldn't get too deep into it, but I think white box is probably the most well-known ones. One of them is Energy Plus, as mentioned. HOT 2000, even though the source code is not known to us, it's not open source. There is like the calculations come from F280, so it's a known also model. There is eQuest, for example, lots of the common industry tools. So white box being the most common. Black box models are more research focused. There are also some, for example, Kaggle competitions. That is like a data scientist competitions, in case you haven't heard of them, that encourage people to do modeling of that sort. And there are some great building challenges if you go and take a look at them. And then gray box also, we have mostly seen it in research, but we were able to develop one for the real world scenarios. Now, about the question you have, Ruslan, about what type of study did we go with. So in our study, we primarily compare our gray box developed model with the baseline of the truth that we have, which is the white box HOT 2000 model. And that's actually a really good segue to our methodology section. So what we wanted to do is to take a look at our building stock, like the buildings that we could find that we could either get their EnerGuide score or actually go on and actually do assessments on site for these homes. And we wanted to know how well our overall process. So in Properate, the R.E.A.L system, the gray box system is the core, but then the overall process that we have that we're going to expand onto a little bit, that is built around all of this gray box technology. How well can it provide results compared to an on-site EnerGuide evaluation? We basically got all of a set of homes that we could get the EnerGuide scores. Basically, looked at our own system. We tried to do a virtual rating on these homes. We tried to do a remote rating on these homes. It wasn't possible for all of them to do a remote rating, so we only did for the ones that we could. And then we wanted to compare the results with this ground truth white box EnerGuide model that we had in mind. None of the homes were previously seen by Properate, and by seen we mean they weren't like, we didn't know their scores beforehand. It wasn't put into our system in any possible way. So all of it was new. Now, the homes that we could find for virtual rating, so enough data about the homes and also knowing their EnerGuide score that we could have a comparison, is 6,917 homes. This is the largest study of its own kind that we know. Would love to see any other examples if people have. For 1,351 of them, we had remote ratings. We get into how we do the remote rating, what kind of data we need about it. But in terms of building characteristics, the smallest home was only 9 square meters, so tiny home, 95 square feet. The largest home was about 14,000 square feet, so a big mansion, very, very varied in terms of the sizes. Climate zones 4 to 7, so milder, the mildest climate in Canada towards like the cold climate. The year builds of the home spanned from 1895 to 2022. There is a bit of a data skew when it comes to year build, so we have a lot more data from newer homes compared to the older homes, but there is a span of the data that we had available. And finally, the buildings were all in Alberta and BC. Now, these Western Canada regions, they have a wide variety of climates, but the construction practices are specific to the regions. Like they are more broad in the North America, there are wood frame construction homes, but in Eastern Canada, we see more masonry buildings, not very common in Western Canada. So that can be a source of limitation for this study. Essentially, this is really applicable to wood frame buildings. So looking at virtual rating, the virtual rating we did was, again, completely touchless. We made a full energy model for every single home with a few more guesses. Now, in the right, you see an example. This is not the actual study pictures. This is an example of how we do our virtual ratings. But because these buildings were spread out across BC and Alberta, so we had like individual models from nearly 7,000 homes. For this virtual rating, the only data that we had available and we had given to our system was the building address, satellite imagery, and some property records that you can typically find from tax assessments or from real estate listings. So something that is very commonly available for individual homes. And then we extracted, so our system gave us an estimate of the score and we could compare it with the actual on-site data. The second tier of rating that we did was through Properate remote rating. So the remote rating, you can see how it works if you go to properate.io, which is our website. This is already, it has been live for a very long time now, that you can put in the address of your home, and depending on the condition of the home and the data available, it will ask you a number of questions. So for the remote rating piece, in addition to the building address, satellite imagery, and property records, we also had some data about the building massing. We had data about the fuel type that was inside the home and the upgrades that the homeowners had done to their home over last decade or so. And that was also, we added this additional data with the original set, gave it to our engine, and saw how the results, where the errors fall into. Now, what do we mean as error? We have on-site rating data. This can be what the energy advisor has gone to the site and they have come up with. And we also have an estimate that our engine has put out. The difference between these, subtracting them with each other, for example, in this case, we have thought it would be 92, it ended up being 86, so the difference is 6. And our ideal scenario is, 0 would be the ideal error rate, of course. Doing this for all of the homes, it gives us somewhat of a histogram, so how close they are to the ideal. And then we can tally all of these individual data points using some error measurement techniques that are common in the energy modeling and performance assessment industry. In particular, we used mean bias error, mean absolute error, normal, and the root mean square error to find the metrics. Now, the difference between these is that the mean bias error and mean absolute error tell us a linear idea of how much the error is. For example, on average, Properate might overestimate by certain amount of gigajoules. And then the weighted error, the one you see on the right of this screen, this is meant to penalize larger errors, because in reality, the on-site assessment is not a perfect science. There might be a little bit of a variation, and we are not really interested in getting the exact same point. Like in this case that I provided, that we said it was 92 and it was actually 86, it's a lot more favorable to get like a score, for example, 88 or 90, as opposed to getting a score that's like 150. So that should be penalized when the errors are larger, and that is what the root mean square error does. Now, the word normalized there, it really has to do with changing from a gigajoule amount to a percentage amount, because people want to know what is the percentage of the errors, and the gigajoule specifically may not make a lot of sense. Accuracy in the context of our white paper is just basically 100% minus the errors. In this case, we again have an absolute accuracy that tells us, you know, what was the exact difference, and a weighted one that penalizes larger errors if you have a lot of them. This is probably the most boring slide of the whole presentation, but it was important for us to bring the table to the slide the way we have it in the white paper so that it makes a bit more sense. But VR here stands for virtual rating, and RR stands for remote rating. So for all of the homes that we had, the scores, we had, you know, all of the homes we could do a virtual rating. But this additional data that we were asking from the homeowners, you know, the additional data we extract from whatever we had, which was the building massing, the fuel types and whatnot, we only have it for about 1,300 homes. So looking at the errors, I'm going to really skip to normalized values because I think people understand like percentages a little better. In terms of the mean, and going to the next slide, which is a histogram of the errors. So we kind of have put all of the error ranges in this graph, and the dotted line here is perfect. So the larger of a column you have closer to the dotted line, the better it is for you. If you look at the virtual rating, you see that the peak of these distribution of errors, it's a little bit offset from the perfect scenario. And you see that in this table as well, that the mean bias error and the mean absolute error we have here, there is a bit of a difference. There is like the model is kind of biased to overestimate the ratings. And then looking at this model again, you see that the remote rating, meaning that additional data from the users, it actually has made it much more aligned with the perfect line. So we have essentially eliminated our model's bias. Like on average, our model is exactly what is EnerGuide predicting. And then there is a lot also of a normal distribution here that we have when it comes to remote rating compared to the virtual. So those few additional questions that we ask from the users, they tend to be bringing the accuracy, clustering it down and making it a lot more predictable. In terms of representativeness of the data, because of the volume of the data we had, the thousands of the homes that we could gather, there is a very high confidence level and a very low margin of error when it comes to this kind of a study. However, because of the data skews that we were dealing with in the building age and the regional, like only Western Canada restrictions, we don't think this data is completely representative of all building stock across Canada, but still it should give us an idea about how accurate the energy models can go. So to give an idea of how accurate we can go there, looking back at this table, you know, in terms of accuracies, so 100% minus the error, that was what we're coming down to. So the absolute accuracy or the linear accuracy that we looked at was, we were about 94% accurate compared to an EnerGuide assessment when you were looking at the individual errors and then averaging them. When we went to weighted accuracy, the accuracy jumps down because there are some substantial errors in the data. As you can see in this our distribution table as well, like there is a lot of these columns that are far away from the perfect line. At the end of the day, they don't really create a huge decline in our accuracy. Like they don't penalize our accuracy a lot. They only for a certain amount. But the weighted accuracy when it comes to virtual rating is about 91%. Now, having those few additional questions asked in the remote rating pushes up the accuracy of the remote rating to 95.5%, and then also slightly improves the weighted accuracy. But essentially, these results have been very encouraging for us because we feel that just using very instant energy rating technology that we have developed, we can really accurately measure and guess how well a building is going to perform in its on-site assessment, and then use that information to really direct the on-site assessments towards the homes that we think they have very high potential, and then verify the results that we have with that on-site assessment. And if that's the case, we can move on to performing home upgrades, planning deep energy retrofits and whatnot. As for the context, our initial objective to just be above 80%. So these results are very, very encouraging for us. Next step for us are to continue our accuracy audits and studies. So right now we have 2 independent third-party verifications that are on the way, and more is also welcome. So if any of you here is interested to try our system and test it out with any kind of EnerGuide ratings or on-site ratings that you may have access to, would love to talk to you and see how we can also perform a third-party verification for us. We also want to expand our set of tooling, and we want to just basically put our technology in more hands. So if you have any particular use case, we would be happy to look into that. And all of this is available on our website as well. So you can play with the tool, you can take a look at it. It's completely DIY, it's completely self-served. So you can just go and start like putting in a home address and see how well it works. Inquiries, questions, be sure to pick up Nora's email, my colleague, and have a chat with us. We'd be happy to talk about all of these really new, emerging, and exciting remote energy modeling and community level energy upgrades landscape that's emerging across Canada. So with that, I want to really thank you, and just gonna pause for any questions that people may have. So feel free to put your questions in the Q&A or in the chat, and we'll be happy to answer it. Okay, question, and this is actually a very good one. So talking about kind of the weighted accuracy, what does it represent? I understand this is like a little like confusing for, if you're not in the literature of it. So the weighted accuracy is not necessarily meant to represent an exact number. So it's like 91% doesn't really mean anything. It's the penalization that really matters, is that, larger errors because what we are essentially doing with the error is that we are squaring every single error we have. That means that if you have a lot of large errors, they exponentially start to increase your amount of errors. So what we will see here that's encouraging is the relationship between the absolute error and the weighted error. The absolute error is something that people understand a lot more intuitively. And it's that when we say our absolute accuracy is 95.5%, it means that if you take all of these differences, like, the EnerGuide number is 100, our number is 95, so we are 95% accurate. If you pick up all of the numbers from all of the 6,000 homes, or in this case, in the virtual rating, and then average them out, you get to 94. Now, for weighted accuracy, what it means is that if you square all of those errors, you get to 91. It's not very intuitive why a squaring, except for the case that we are trying to penalize larger errors, and then see how much we fall off from the absolute accuracy, if that makes sense. Happy to answer it more. Another question, as a part for the white box approach, do you conduct any physical measurement, infrared camera, indoor temperature record, etc. on site? Ruslan, this is a very good question. One thing to understand here is that these kind of energy modelings are specifically made for what we call non-temporal building assessment. Non-temporal assessments really have to do with how the building itself actually is, and they try to take away the occupant behavior as much as possible. So if you go in a home and, for example, look at the indoor air temperature or look at infrared camera readings, these kind of things might be related to the occupant behavior, as in the amount of the set point temperature that they put for their thermostat, or like how they, operate their windows, that sort of thing. And because people have very different metabolisms, and they also have very different patterns of using the home, the energy rating you're going to get is going to be different from homeowner to homeowner. We try to take all of that uncertainty out, because when we are talking about community scale building energy upgrades, people might change homes. People might rent a home and then stop renting it, and somebody else comes in who likes the home a lot warmer and a lot cooler, or a lot cooler. So we don't want the energy rating of a home change between different occupants. And that's why we try to take those individual like temporal readings as much as possible, take them out as much as possible, and only focus on our values, only focus on, for example, like the air tightness of the building and whatnot. That said, on-site assessments by design, they have a number of these features that you talk about, just because of using the opportunity that somebody's at home and they can benefit from it. And in some cases, it also has to do with non-temporal aspects of the building's usage. So for example, when an energy advisors come on site to your home, they have a blower door test device. They push a lot of air inside the home, and they see how fast that air leaks out of the home. So get an idea of air tightness. A lot of energy advisors provide infrared camera outputs for the homeowners. They take pictures of different parts and share it with them so that they know where the things are escaping, where the heat is escaping. And indoor temperature records, that sort of things are also somewhat easier to come by. We generally tend to think that these are auxiliary to non-temporal assessments. And actually, like Properate has had a push for libraries to provide, thermometers, thermal cameras, that sort of thing to homeowners, so that they can get a better idea of their own home in a DIY fashion, in addition to that non-temporal analysis. Avi, we'll be happy to talk to you. We will talk to you. If you can, please put your email or something inside our system. Darla, David, thank you for the kind words. Happy that this was helpful. Now on to Kenny's question. On average, how long does a typical remote assessment take compared to an on-site assessment? That's a really good question. So if you go to our website, you see that depending on the home you're inputting, the number of questions may be different, because we are really asking you for what we don't know. The number of questions can be anywhere between 4 to, I would say, 10, 12. But the benchmark that we provide, like the idea that we provide, is that the remote rating takes about 5 minutes of a homeowner's time. And that should be just enough to really give a good idea. So it's a really good use of time, if we may, compared to an on-site rating that, based on the availabilities or based on the amount of work that's involved, it may take a lot more time. So we really want to maximize the amount of time that we put on-site, maximize the benefits of it by really trying to target those on-site assessments using remote ratings. Knowing that we are at time, I have to stop here. So thank you so much for joining today, and I hope you have a great rest of the day.